Okay, so we've learned, yesterday we went through those properties of transformations of quadratics. So now we're kind of going to summarize here for these particular ones. All right? So, and we're going to try to do these, at least some of the properties, without graphing on our calculator. So, direction of opening. Remember that negative leading coefficient means it's been reflected in the x-axis. So that means it's going to open down. Okay? Vertical stretch factor. Remember, it's the absolute value of that number. So that means positive 2. Okay? So if it's stretched by a factor of 2, is it narrower or wider? That means that y value is now higher up, so it's narrower. I'll just use n. Vertex, you look, is there a number added or subtracted with x before the squared? There isn't, so it's 0. And the number added afterwards is the new y value of the vertex. Okay. So graphing it, we can do a little sketch. Actually, let's do this. Okay, so 0, 14 is up here, and we know it's opening down. Okay, it's just a sketch. Axis of symmetry, remember that's the line, vertical line that cuts it in half. So that's going to be the y-axis here. The equation of the y-axis is x equals 0. The domain for all parabolas that open up or down is x element of the set of reals. So that's going to be the same all the way down. Right? The range depends on the vertex and what direction it's opening. So that vertex is at 0, 14, right? That's 14, and it's opening down. So your range is going to be y less than or equal to 14. Okay. And then the max min y value and the x value when it occurs. So really that's the vertex, but we're separating it. So is this a maximum point or a minimum point? It's maximum because it's opening down. So the maximum value is 14. Okay, when does it occur? When x equals 0. Right, those are from the vertex. Now, x-intercept. We could find it on our calculator. We can find, for this one, we can find it algebraically as well, actually for all of these. We haven't done a lot of that yet. We're going to spend a lot of time. But remember, the x-intercept is when y is 0. So if I put 0 in here and solve for x, I could bring this over, and I get x squared equals 7. So what are the x-intercepts? Hands up. Yep, x squared equals 7, so that means you have to take the square root of both sides. So that would be equal to positive 7, negative 7. So we can show that as plus or minus 7, root 7. And the y-intercept, easy to see, it happens to be the vertex. So that's 14. Okay. All right, so let's do the third one. You're going to do the second one on your own. Let's do the third one. Okay, so here, direction of opening, we look in front of the x squared. There's nothing shown, which means it's positive 1. So it's opening up. If there's a negative, it would open down. If there's no number there, it means it's a 1. So that means it hasn't been stretched at all. Okay, you can leave it blank or not applicable. So is it narrower or wider? Nope, it's the same. The vertex, remember from yesterday, opposite sign of the constant, so -2, and same sign as the constant outside the bracket, so -16. Okay, so then -2, oh, I want to actually do, I want to go, so -2, -16, kind of down there, and then it's opening up. Okay, that axis of symmetry, remember, it goes through the vertex, the vertical line. It's always x equals whatever the x value at the vertex is. Domain is all real numbers. Range, you take a look at the y value. So here it's opening up. So it's going to be y greater than or equal to -16. So because it's opening up, that vertex is a minimum point. So it has a minimum value of -16 at x equals -2. Then for the x-intercepts, so that would be 0 here. So we want to bring the 16 over. Okay, then we want to square root. So square root of 16 is 4, but remember it will be positive or -4, just like we did here. That ended up being positive or negative √7. Okay, so two values, x plus 2 equals positive or -4. So if it's positive 4, then when we bring the 2 over, 4 minus 2 is 2. If it's -4, we bring the 2 over, it's -6. So you've got two x-intercepts. One is at 2, and one is at -6. And then the y-intercept, that's when x is 0. So put 0 in there. 0 plus 2 is 2. 2 squared is 4. 4 minus 16 is -12. And we'll do one more. We'll do the next one because it has a half in front here. Okay. So half in front is a positive number, so it's going to open up. That value, a half, is less than 1. So that means it's going to be wider. Your original y value will be multiplied by half. So this is a vertical stretch factor is a half, and it will be wider. Okay, so then the vertex is opposite sign, +5, 2. Okay, so 5, 2, and opening up and kind of wide. Okay. So your axis of symmetry goes through the vertex. It's going to be x equals 5. Domain is all real numbers. Range is opening up, so it's going to be y greater than or equal to. And you look at the y value at the vertex, 2. So if it is opening up, that vertex is a minimum point. So your minimum value is 2 when x equals 5. Okay. Are there any x-intercepts? No. Just look at the graph. There aren't any. And if you didn't know that algebraically, you would bring the 2 over, okay, be -2. You divide by half, so it would be -4. Then you would have to square root -4, and you can't, right? So there's no x-intercepts. Y-intercept would be 0 in here, so that'd be -5 squared is 25 over 2, which is 12.5, or 25 over 2, plus 2 would be 29 over 2 as a fraction, or what's that, 14.5. All right, so you're going to do the missing lines there. We're going to look at the next questions, okay? So go to the next page, and it says make a sketch, label the vertex, and state the number of x-intercepts. Okay. Try to do it without a calculator. We'll look at our calculator in a bit, but here let's do. Let me just graph some x and y. So good idea to have a straight edge with you, just in case you have to sketch something. Okay, my hint, if you have a little bit older version of the calculator that uses normal batteries, there's a straight edge. Okay, so you're not going to have to measure anything or show a scale, but your x and y axis, they shouldn't be like wobbly. Okay, so use that if you can. So here, vertex is -1, 3. Okay, so -1, 3, and it's opening up. Going to be skinny because of the 5. So just, you don't have a scale, but just make it kind of skinny-ish. Depends on your scale, right? And then, so I would label -1, 3. Okay. Doesn't cross the x-axis. Does cross the y. So I would figure out what the y-intercept is and also label it. So when x is 0, that's 1 squared is 1, times 5 is 5, plus 3 is 8. So important points to plot are the vertex and any intercepts. Okay. State the number of x-intercepts. As I said, no x-intercepts. So basically, if you know it opens up and your y value is bigger than 0, there's no way it can come back down, okay, to cross the x-axis. Then here, the vertex is -7, 0. And it's opening down. So here, you could label the point, or if it's on the x-axis, you can just label -7, because that's a point on there. Okay. Often, actually, we show it below when we are showing a scale. Okay. Okay. What would the y-intercept be? -49, exactly. So if we extended this all the way down here, it would be at -49. Okay, because that's when x is 0. In this case, it says how many x-intercepts? Well, this just touches once because the vertex is on the x-axis. So 1 x-intercept. And then here, the vertex is +3, 6. The negative leading coefficient means it opens down. Okay, so +3, 6, and opening down. Kind of skinny-ish. We might need to change that once we find the y-intercept. Once we know if the y-intercept is positive or negative, I might need to make it a little bit wider. So label the vertex. Okay. Y-intercept is when x is 0. So that would be 9 times -2 is -18, plus 6 is -12. So actually, we can keep that. In terms of the x-intercepts, those would be radicals, okay? Because you would have 0, you'd bring this over, divide by 2, so you'd have √3 plus or minus √3 plus 3. It doesn't say to actually label the x-intercepts here, okay? So we're not going to bother with that because we're going to spend more time finding those tricky exact values. But that has 2 x-intercepts, and that's what you're asked to find out. Okay. So those were some actual examples that will help us with the next question. So the next is that vertex form. Okay. And we want to state what conditions apply. Are A, P, and Q positive or negative or 0, that kind of thing. Okay, so here's an example that had no x-intercepts. We looked at that, we knew that it opened up and the y value was greater than 0. Okay, so that means A was positive and Q was positive. Doesn't matter where P is, right, horizontally. So we could have A greater than 0, P greater than 0. Oh, sorry, Q greater than 0. Actually, I'm going to use the word and because we've learned about that, right? Both conditions have to be met in order to have no x-intercepts. What's another possible situation? Both negative. So if we had a vertex, say here, and it opened down, then your leading coefficient is negative, so A is negative, and your y value at the vertex is negative. So you could have A less than 0 and Q less than 0. Okay, but not a combo of both. Okay, what about B? Say it again. No, because you can't have one positive and one negative. So they have to go together, right? So if you say that this can equal 0, then this could be negative, right? But if it's negative, that Q has to be negative in order to have no x-intercepts. So that's why you have to split it into the two cases, both positive or both negative. So x-intercepts, one x-intercept, what condition? Q equals 0. The y value has to be 0. We'll give you a vertex on the x-axis. So that's it. Okay, and then 2x-intercepts, well, what happens? So here, the y value is positive, but the a value is negative. Okay, so the y value at the vertex is q, so, and a was negative. So we can say a less than 0, and q is greater than 0. Okay, are there any other conditions that might work? Yeah? Yeah. Okay. So one positive, one negative, and vice versa. Again, doesn't matter about P. Okay. All right. So kind of back to yesterday's about the transformation. Take a look at the definition that's given there. Image point. The point that results after transformations have been applied to a point on the original graph. So where does it end up, that vertex that we started with? After we do the stretch and reflection and translation, where does it end up? That's called the image point. The whole graph after that is called the image of the graph. You'll talk, as I said, in 30-1, you're going to do a whole bunch of work with transformations of all different functions. So that word will be used regularly. So we're just trying to get you used to it. So the graph of y equals x squared was transformed to that new graph. Describe the transformation. So that's where we use those words, right? So we look for, you got to do stretches and then reflections and then translations. So we look at the coefficient in front. It's negative 1/4. The stretch is just 1/4. So we say vertical stretch by a factor of 1/4 about the x-axis. Okay, so that's the first thing. Then if there's a negative out front, you do that. That's a reflection. Reflection in the x-axis. Then we do translations. So there's two. There's one horizontal and one vertical. So it doesn't matter which order you put those in. So horizontal translation. So x plus 1. Which direction have we moved the graph? Left 1. Good. And then a vertical translation. The plus 6 outside there would be 6 units up. Okay. So that's what I would expect to see if we asked you that on a test. Okay. I didn't use any abbreviations like I did yesterday. Now, in Math 30-1, you'll also be doing horizontal stretches and reflections about the y-axis. Okay, really with parabolas, because they're symmetrical about the y-axis, we never show a reflection because it ends up being the same and before you move it. And then same with the horizontal stretch, can be shown as a vertical stretch. We'll talk about that as we go through the course. So we really end up, because we often show it in vertex form like this. Okay, so now here is a question where we have to find the image point. So negative 2, 4, right? When we put negative 2 in there, we get 4. So that's a point on our original. What happens to that point if I do all of these transformations on it? So what I do is I go through each of these. So if I start with this and do a vertical stretch by a factor of a fourth, my new point is going to be negative 2, 1. The original y value multiplied by 1/4 is 1. Then when I reflect in the x-axis, that changes the sign of y. And then when I move that 1 unit left, if I'm at negative 2 and I go left 1 unit, now I'm at negative 3. And then if I go up 6 units, my x stays the same, and negative 1 plus 6 is 5. Okay. So that's the image of negative 2, 4. So you do the next one. Do the same thing, but with the 0.39. Sorry. 6 units up, 24 minus 9 is... Well, I kept it in fraction form. You can, because that is a terminating decimal, you could show it in decimal form. But if it was, say, 1/3 or something, then I wouldn't, because it was, you'd have to round it. Okay, and then last one. Okay, vertex. So this is in that vertex form, so it's going to be positive 3, negative 7. Then it says, algebraically show that the parabola passes through this point. Okay, this is how I show that. I don't know for sure, pretty sure it's that it does show, but I don't want to make it equal yet. So I want to take the left side of my equation and the right side of my equation and substitute the values in. So the left side is y, so I'm going to enter y in there. My right side is 2 times x, which is 3 minus 3. Oh, sorry, this has got to be 6. Sorry, I'm looking at the wrong point. 6 for x minus 3 squared minus 7. 6 minus 3 is 3. So 2 times 9 is 18 minus 7 is 11. So yes, the left side equals the right side once I substitute those in. Keep them separate until I know for sure that they're equal. Okay, use symmetry to determine the coordinates of another point on the parabola. So that's where, think about what it looks like. Okay, my vertex is 3, negative 7. Okay, it's opening up. And another point, what would the y-intercept be? Yeah, so it's going to be up here. Okay, so a point, I'm just going to extend this further. Oh, just a sec. Okay. Oh, that's not good. Just a second. There, that's pretty good. Okay, so 611 might be here. This vertex was 3, -7. Okay, remember what we talked about the other day? Another point would be symmetrical about the axis of symmetry. So if I graph the axis of symmetry there, then drew a horizontal line from here to here, then this distance, so this is at 3, right? So 3 to 6 is 3 units. This unit here, this distance would be 3. So actually, that's your y-intercept, okay? So I should probably fix this a little bit, more like that, right? And so what's your y value there is 11. Okay, so another point would be 0, 11. That we used symmetry, okay? Turned out to be the y-intercept. If we had just substituted 0 in, that would give us another point, the y-intercept, which turns out is this point, okay? So you don't have to use symmetry to get another point, but it certainly helps.